So welcome to the second Solar Climate Intervention Symposium. So these are 1 hour sessions where researchers share their work on solar climate intervention. So if you would like to present, please reach out to either me or Simone Tilms. I'm hearing some feedback, so yeah. Okay. And so, yeah, if you have any questions for the speakers, please feel free to put them in the chat, or there'll be time after each talk to ask the questions. So first up today, we have Susanne Baur from CERFACS in Toulouse. And she'll be speaking about the deployment length of solar radiation modification and interplay of mitigation, net negative emissions, and climate uncertainty. So Susanne, if you want to go ahead.
Cool. Thanks, Matthew, for the introduction. Yeah, exactly. I want to present some work that we've done on determining SRM deployment length in a specific setup, of course, and how this length is determined by mitigation, CDR, and climate uncertainty. So the setup that we're looking at is this buying time approach or peak shaving approach with this napkin diagram that most of you have probably seen more than just once, where we're having an overshoot scenario over target temperature. Here it's 1.5, and we're using SRM to stay below that target until the emission scenario would reach the target temperature again without SRM. And so the question we ask is, in such a setup, how long would we deploy SRM, and what is this length dependent on? Yeah, as I will be using the word SRM deployment length a lot in this talk, at least on the slides, I abbreviated that with SRM DL. Okay, so the length is, of course, highly dependent on the data, the scenarios that we're using, and so I want to take enough time to explain what we did there. So we're using pathways from the recent IPCC report Working Group 3 database that are in line with the 2030 nationally determined contributions. So they all start under similar conditions in 2030, and then these pathways digress to different states in 2100. We run the simulations with MAGIC 7. It's a reduced complexity climate model, and we're using it in its probabilistic setup. So all 600 ensemble members. And yeah, so each scenario from the IPCC database that is NDC aligned is run with all 600 ensemble members. So that gives us quite a lot of realizations, 213,000, with, of course, extremes of what climate uncertainty has to offer, but also just very different degrees of mitigation and CDR. And so the setup of the study is then to extend these emission pathways until 2500 and to find for each ensemble member of the MAGIC range the radiative forcing that would correspond to a 1.5 trajectory, so the SRM trajectory. Because then the SRM is simply put, the difference between the ERF of the emission scenario and the ERF of the SRM trajectory. It's in reality, of course, not as simple as that, but that's the basic idea behind the calculation. And the earliest start year for SRM we set to 2030. So a few more details on the extension. We put the emissions data into 3 categories, so fossil and land use CO2 and non-CO2 forcers. So that includes methane, but also like aerosols and things like that. And for these non-CO2 forcers, we make the assumption that they just stay constant at their 2100 level because they contribute only very little to the total amount of warming. For fossil and land use, or follow CO2, we get a little bit more creative. Here I'm showing the extension for fossil CO2. So this is what we got from the NDC scenario. And then we set up a distribution for a maximum CDR that can be achieved from and that can be achieved in one specific scenario. So we randomly sample from this distribution, and I'm saying CDR, and I put CDR on the slide because that's more the term that is commonly used and understood. But what it means in our study is net negative emissions. So a lower bound on CDR. True CDR would probably be higher than that. And we chose a log normal distribution just to account for the fact that 40 gigatons annual removal is less likely than 10. So the median is set to be 15 gigatons. So for each of these 355 scenarios, we randomly assign a maximum CDR amount, and we linearly extrapolate with an increase in the decarbonization rate of 0 to 3%, also randomly chosen, the trend of the last 5 years of the 21st century until we reach that maximum CDR that we assigned to that respective scenario. For land use CO2, it's similar, though not exactly the same. So here you can see that most scenarios from the IPCC database already have a substantial amount of negative land use emissions by the end of the century. And so also, according to literature, the potential to remove CO2 with land use-based measures could be already exhausted or saturated by the end of the 21st century. And so here we just chose like an emission floor that is a normal distribution between -1 and 1 gigatons to be sort of not exactly 0, but close to 0. And we also randomly sample from this. And in contrast to fossil CO2, here we have a time limit as to when we want this emission floor to be reached, and that is 2150. And so these pathways basically have 50 years to get to their floor level, and then they just stay constant there. Okay, so now we have the emission pathways, and we need to translate this into radiative forcing and temperature. So we need to run the scenarios with MAGIC. Before I show you what it looks like translated into temperature, I want to explain the uncertainty range that MAGIC gives. So MAGIC has uncertainties related to various processes such as climate sensitivity, aerosol effects, ocean processes, carbon cycle, and so on. And each ensemble member of these 600 has different assumptions regarding these uncertainties. And so that makes up the climate uncertainty plume that is the output of MAGIC. But what this boils down to for us is how do emissions relate to temperature change? And there is a metric that tries to describe that, the TCRE. And the TCRE basically just relates temperature change to cumulative emissions. And so in our scenarios, we have positive emissions and we also have negative emissions, right? So we calculate a metric for positive cumulative emissions, which we call TCRE up, because the temperature goes up. Basically, that's the normal TCRE, and a TCRE down for negative emissions. And TCRE up and down are not the same, they're not linear. And so that means that the efficacy of positive and negative emissions on temperature varies. So positive emissions could be more efficient at warming than negative emissions at cooling, for example. And this is important because it affects how efficient CDR works, how much gigatons have to be removed to compensate for the positive emissions, which of course influences SRM length. And so metric we look at in this paper is the ratio of TCRE up and TCRE down, but I'll get to that later. Okay, so that just to explain the climate uncertainty aspect. And going back to the emission scenario, when we run this with MAGIC and we look at what that translates to in temperature, we get this. So this is the 5th to 95th percentile of all pathways and all its realizations. So it is basically climate and scenario uncertainty. If we just look at what climate uncertainty range would give us for one pathway, this is sort of the range that we get for one pathway, only entailing the climate uncertainty, so the 600 ensemble members. And yeah, just to get an idea of the general ambition, let's say, of the scenarios, in here, the median peak warming of all those realizations is at 2.1, so not extremely high. Okay, so now I'd like to show you some results. First of all, looking at the spread of SRM deployment lengths that we get for this large range of realizations. 5% of pathways actually never deploy SRM because they never overshoot 1.5. And then there's 15% that deploy SRM after 2,500, so longer than 470 years. It's 470 because we start SRM earliest in 2030. And this is the distribution we get in between this range, and we can see that most pathways require around 150 to 300 years of SRM to stay above 1. To not stay, to avoid going above 1.5. And the small boxes, the black boxes at the bottom, represent pathways that are aligned with current 2100 warming projections for the NDCs, so 2.4 median warming in 2100. And you can see that even that none of them deploy SRM for less than 100 years. So even in the most optimistic assumptions regarding climate sensitivity, carbon cycle, and so on, and none of them would deploy SRM for a shorter time than that. The extremes of no SRM and SRM past 2,500 are of course interesting, but we're really more interested in the range of 1 to 470 years and how different mitigation levels and CDR assumptions influence that. And so in the next plots and the next things that I will show you, it's just this range of 1 to 470 years. Okay, so starting with mitigation, here we're looking at cumulative positive emissions until net zero. And it's color-coded by different levels of average annual net negative emission. So NNE means net negative emission, or CDR. Blue are rather low annual CDR levels, green high, and red really high. And so as you can see, you don't really see much. And that's because you're not supposed to. There's actually a weak relationship between mitigation and SRM in our scenarios. And that means that here, mitigation strength doesn't really constrain SRM length very well. Moving on to the negative emissions in CDR. So here I'm plotting cumulative emissions from net 0 to 1.5. So mostly negative emissions. And what we're plotting is the burden. So this is how much needs to be removed to arrive back at 1.5. And this is what it looks like. So low cumulative emissions are represented across the whole range of SRM deployment length, whereas the high cumulative emissions are constrained to the long SRM deployment lengths. That means the requirement of cumulative negative emissions bounds the commitment to SRM, so to say. And so adding to that burden, our capacity to actually remove carbon, so our annual net negative emissions, the plot looks layered like this. Now this is average annual negative emissions. So the number that you see here is not the actual CDR that is deployed in the last years of SRM. It's not the maximum amount that we assigned, but an average over the whole time of its scaling up. And there are some well, there's some interesting areas in the plot that I want to highlight a little bit. So first we have this very obvious triangle shape here that is not covered by data at all, except some weird outliers. And that is for two reasons. First, the time that it takes to scale up CDR. So it's just not possible to only do SRM for, I don't know, 20, 30 years. And in that time frame, scale up net negative emissions to very, very high levels. But also it's because of the limit that we set on maximum net negative capacity. So the 40 gigaton CO2 annual removal. So I guess if we had chosen an even higher limit than 40 gigatons, this area of the plot might be covered. And yeah, here it's quite clear that in general, the higher the annual removal, the shorter the SRM deployment. And so these scenarios, for example, very rapidly scale up their CDR, since in only a few decades, they end up in like a range of 15 to 25 gigatons average removal. And these scenarios here are really mostly scenarios that have very small overshoots. So we didn't set any limits and said that as soon as 1.5 is overshot, the scenario is in the group that we want to look at. So these often have overshoots of only like 0.01 degrees Celsius or something like that. Okay, so much to mitigation and CDR. Now to the TCRE. So here on the y-axis, we have the ETCRE ratio, and it's color-coded by the year of reaching net zero CO2. So yeah, the higher the ETCRE ratio, the lower the sensitivity to negative emissions compared to positive ones. And that means that in those cases, negative emissions are less effective at cooling down than positive ones are at warming. And looking at the year of net zero, we see that we have longer SRM deployment for scenarios with high ETCRE than for low TCRE, even though net zero is hit earlier, which sort of makes sense, right? But in general, we don't really understand the underlying mechanisms too well here, and the ETCRE metric that we calculate is also not very clean, and so it's a little difficult to draw conclusions from it. But yeah, so coming to the conclusion, let me highlight a few aspects. So we get a large spread of SRM deployment lengths for scenarios that start under similar conditions, and realizations that follow current NDC median 2000 warming projections 2.4 degrees. None of them deploy SRM for a shorter period than 100 years. And the length of SRM itself is very much dependent on mitigation, negative emissions, and climate uncertainty, but none of these factors alone can really predict how long an SRM deployment is or will be. And even more startling to me, SRM would be started without really knowing how positive emissions evolve under it, and without knowing what our actual capacity to remove carbon is, and the whole uncertainty related to climate reversibility and so on, which makes it actually almost impossible to predict beforehand how long the SRM deployment will be. And with that, I want to thank you for your attention and the opportunity to present my work. And yeah, looking forward to some questions.
Thank you very much, Susanne. Does anyone have questions? Please feel free to unmute.
Andrew Lockley, isn't the damage function much more closely related to the slope of the temperature change than the absolute value of the temperature change? Because people get used to higher temperatures, and therefore, other than sea level rise, the economic damages are not closely linked to current temperatures, and therefore it's kind of hard to see why people would sustain SRM for 400 years unless it was specifically to hold back the sea, right?
Yeah, I understand your question. And that's why I highlighted in the beginning that, I mean, these results are, of course, only related to if you want to do this peak shaving thing. But even if you wanted to phase out earlier, or only reduce the increase in temperatures, you'd still have to do it for several decades, and you wouldn't know for how long you'd actually do that, because you don't know where you will end up. So I mean, in the end, it's the same response. You wouldn't know when you start how long you have to do it, and so how much it costs, all these things is really uncertain or unknown, impossible to predict beforehand.
So Alan comments that the original napkin diagram had a length of 150 years, which agrees completely with your results.
Nice.
Could I ask another question, maybe?
Go ahead.
Of course.
Thanks a lot, Susanne. I thought that was really insightful. I just wondered if you could maybe expand a little bit on this notion that the mitigation, sort of the speed of mitigation, or that mitigation characteristics do not influence the length of SRM that much. I didn't really catch why that's the case.
Mm-hmm. Okay, so you're speaking about this plot. So this mostly is due to the uncertainty related to the TCRE up and TCRE down. So one reason why this plot looks so stratified is because it's basically how do I explain this? So one line here is one scenario, and the single dots are each ensemble member in that scenario. And so we get this whole spread here because of the spread in climate uncertainty that we have. And of course, there's a skew towards shorter deployment for low positive emissions rather than towards this end. But still thinking that, you know, you're only going to emit, you're only going to have few cumulative emissions during your SRM deployment, and that's going to ensure that your SRM deployment is going to be short, is a daring assumption to make, because we don't really know where the peak warming will end up and how long it takes to go down.
Yeah, so is there something like basically the freedom we have in how much mitigation we do is smaller than the uncertainty in climate sensitivity? Is that sort of a good?
Yeah, that's a strong assumption to make. I guess it's what this shows really, it's easier to set a lower bound on the SRM length than an upper end. I mean, that's also because of the limit of 470 years that we chose, but it's basically easier to say for this, it'll be at least this, no matter what the climate uncertainty is, at least in the range that we currently get from the IPCC, rather than to say, you know, the complete range is this, or I don't know. So it's easier to set a lower bound. You'll be at least bound to SRM for this amount of years. But yeah, it's clear that it's not really a linear regression here, not for mitigation, and also not for the negative emissions. This is more like a bounding condition.
Simone, do you want to ask a question?
Yeah, I just wondered if, I mean, this matrix only includes timing, right? Not the amount of SRM. So would that make a difference in this plot?
Yeah, so I have been thinking about this too, because we only included timing, not the actual amount. And I decided to disregard this question for this paper, but probably this would definitely make a difference, because, well, you're adding another dimension to it. But I'm pretty sure that mostly it'll be scenarios that have high peak warming, so high climate sensitivity, would deploy SRM for long periods than pathways that have lower climate sensitivity and peak lower, and therefore require less carbon removal to actually go back to 1.5. But there again, it's this interplay between ETCRE up and ETCRE down, which needs to be in an optimal range to be on the shorter end. And I also wondered whether the amount of SRM really makes sense if we're looking at scenarios that cool down 3-4 degrees, whether that is still a super realistic scenario. But yeah, it would be an interesting dimension to add the amount of SRM.
Yeah, thanks. That's really complicated.
Okay, great. Thanks, Susanne. I think we'll move on to Haruki now.
Thank you.
Haruki, can you share your screen?
Sure. Okay. Can you see my screen?
Yep, that's good.
Great.
So now we have Haruki Hirasawa, who's a postdoctoral fellow at the University of Victoria, Canada, and he will present on accelerating exploration of marine cloud brightening climate impacts using an AI implementation of the Fluctuation Dissipation Theorem. So take it away.
Yeah, thank you. So yeah, my name is Haruki. So I'm at the University of Victoria. It's early in the morning here, so good morning. And so I'm going to be presenting today some work that we've been doing in collaboration with some folks at the Palo Alto Research Center, as well as the University of Washington. And I've abbreviated that long title a little bit. And essentially what we're trying to do is use AI to apply the Fluctuation Dissipation Theorem and think about if maybe we can use it to more rapidly explore scenarios in the case of marine cloud brightening forcings. So this is work that was funded by DARPA, and we also used some simulations that were completed with some computing resources donated by Amazon Web Services. Okay, so I'm sure I don't need to explain this in too much detail. So marine cloud brightening is, of course, one of the proposed solar geoengineering techniques that we might need to use in the near or far future. And so MCB is, in particular, what happens is that we would be spraying sea salt aerosols into marine low clouds with the aim of reducing the size of the cloud droplets, thereby increasing the albedo of the marine clouds. And then this, of course, decreases the amount of incoming solar radiation and cools the surface. So in contrast to stratospheric aerosol injection, MCB depends on using tropospheric aerosols. And so MCB aerosols have a much shorter residence time in the atmosphere, so as short as days to weeks. And that means that both the time scale and the spatial scale of possible MCB interventions can be quite a bit smaller than SAI, which is sort of constrained by in terms of time scale by the rate of removal of the aerosols from the stratosphere, and the in terms of spatial scale by the fact that the stratosphere tends to be pretty well mixed zonally. And so this means that, there's a pretty large scenario uncertainty when it comes to MCB, that's even larger than the already quite large scenario uncertainty for SAI. Okay. And so if we want to, fully consider MCB as a potential intervention, it would be nice to be able to fully explore a wide range of different possible forcing scenarios. And the issue with this is that SRM climate impacts are usually assessed with GCMs, which are, of course, computationally expensive, and it can be difficult to coordinate multi-model comparisons in order to assess uncertainty in the climate impacts. And so what we wanted to do is see if we could leverage existing data sets in order to more rapidly project MCB climate responses. And so the technique that we're using here is inspired by the Fluctuation Dissipation Theorem. And so this is a theorem that arises from thermodynamics that says that for certain systems, the statistics of the unforced variations of the system can be used to project the response of the system to small forcings. And so the prototypical example here is Brownian motion, where you can use the random statistics of the random walk of a particle in a fluid in order to compute the diffusion coefficient. And this diffusion coefficient is related to viscosity in such a way that you can use this diffusion coefficient to estimate the drag force and therefore the response of a particle under an external forcing. And so it's been hypothesized that the climate is one such system where the fluctuation dissipation theory applies. And so it's there have been many attempts with varying degrees of success to apply FDT to climate model data. And typically this is done by computing a linear response function. So for example, here for a constant forcing delta F, to get the estimated response delta X, you would calculate these covariance matrices from the internal variability of a climate model output at different time lags, and then multiply that by the inverse of the covariance matrix at the 0 time lag, and then integrate that to some upper time limit here t. And so this gives you a matrix that you can then multiply by the forcing and project and get an estimate of the mean climate response to a perturbation. And so here I'm showing an example from a 2015 paper where they projected the 700 hectopascal temperature response to ENSO-like SST anomalies. So here is the true temperature response on top, and then on the bottom they're showing the projected temperature response via FDT. And so even though we're only considering the linear component of the response, FDT is able to, with a fair degree of skill, project climate responses to some perturbations. But there are, of course, some limitations to FDT. So for one, we do typically use climate model data to compute the linear response function, but this requires a pretty substantial dimension reduction. So typically you would compute EOFs and select the top maybe 1,000 or something like that in order to make the particularly that inverse computable. The FDT is also only applicable for linear responses to relatively small perturbations. And of course, interventions might not necessarily be small. And then we also need to assume quasi-Gaussian statistics of variables. This is not a huge problem for climate, at least. And then finally, typically, at least for climate applications, these FDT methods need to use data from pretty kind of specialized reduced complexity models in order to make it practical to compute the LRF. And so what we wanted to do is see if we can loosen some of these requirements by using AI in place of this linear response function. So in order to do this, we need to consider a little bit of the math behind FDT. So if we consider some initial condition xi, then we define a transition probability distribution of the output field y as w after some time tau. And so if you have some initial condition, I guess in a purely deterministic system after time tau, the y would just be a single value, but because we have round off errors and subgrid scale processes, et cetera, this is in practice a PDF here. And so what our AI model does is it's a regression model at a pretty, fundamentally it's a regression model. And so what it specifically does is that it approximates the mean of this transition probability distribution given the initial condition that we give it here. And so it's expressed as this integral here, where we're integrating over the output field y over this transition probability distribution. And so if we wanted to calculate the climate mean of the output variable, then we can just integrate over the different initial conditions xi of this integral over y, and that means that we can estimate the climate mean by plugging in our AI model here in place of this y and w integral. And then again, we make another assumption that we can approximate this integral over the initial conditions by averaging across many different initial conditions the projected AI model effect. Okay, and then if we then consider some set of perturbed initial conditions where we're adding in some forcing delta F, then we can then approximate the mean perturbed outputs y prime after time tau by, again, instead of by taking the average of the AI model outputs, except now we're just adding this delta F into the inputs. And so then we can quite simply compute the mean change in climate due to a forcing delta F at time tau as the difference between these two sums. And then if we consider that the delta F is a constant, or it's a step forcing that started at some distant time in the past, then the total climate mean impact after some long time lag is computed by taking the integral over many different AI model projections at these different time lags. And so ultimately the equation that we use for our AI model FDT projections is this right here in the gray box, where we're summing first over many different initial conditions x of I, and then we compute the integral or the sum over the different AI lag models. Okay, and so what this allows us to do in terms of FDT is that, at least with the particular AI method that we chose, there's no need for a priori dimension reduction, in the sense that the AI itself is sort of reducing the dimensions when we run it or when we train it. We also don't necessarily need to assume Gaussian statistics, and because we're not explicitly making a linearization assumption, we can in principle apply this method to larger perturbations, and in principle it can capture nonlinear responses to forcings. So the specific AI model design we're using here is a multi-layer perceptron, which is a fairly basic neural network. And so what the model does is it takes in a set of input data that are radiation anomalies, and then it projects 3 selected surface climate outputs. And then the training data is ESM data that is mapped to a spherical icosahedral grid so that it has a uniform area. And so this greatly simplifies the training and application of the AI. So the specific input fields we're using here are the top of atmosphere cloud long wave and short wave, and then the surface cloud long wave and short wave, as well as for clear sky, we're taking both. We're combining long wave and short wave for surface and TOA as well. And then we have precipitation, temperature, surface pressure, sort of the simplest output fields to test. Okay, and so the training data that we're using for our model, of course, we still require a pretty large data set of internal variability to successfully train our model. And so we went to perhaps the largest and most readily available data set of internal variability, which is the CSM2 large ensemble. This is and so in particular, we're using monthly mean data from the CSM2 large ensemble smoothed biomass burning historical simulations. And so that means we have 50 ensemble members of 1850 to 2015 data. And so that means we have about 100,000 months of training data. And so, of course, this turns out to be a good amount and enough. But, we do need this this type of size of training data set in order, especially for some of the longer lags that we're considering, the 30 to 60 month time lags where the signal is relatively small compared to the noise. So before we pass our ESM data, the CSM2 large ensemble data to our AI model, we pre-process it by removing the ensemble mean of the CSM2 large ensemble at each grid point and month in the time series. And so this just gives us the internal variability, including without the seasonal cycle. And the resulting AI model, we train at, we train an individual model at a range of different lags, and then we can evaluate it in two ways. So the first is what I'm calling emulation validation. So this is just validating whether or not the AI model can indeed emulate the CSM2 noise, given the input initial conditions from the model. And so here I'm showing for surface temperature the root mean squared error in the spatial map, as well as here it's the ratio of the root mean squared error and the internal variability standard deviation, where one would be where grid points where the model is essentially performing at noise levels, and then blue would be regions where the model is performing better than noise. And so I guess you can see here that the RMSE is showing that higher errors, essentially where there's higher internal variability, and it's a little bit more interesting to look at this right figure where we see that there's a large patch of blue in the tropical Pacific, which seems to indicate that our model is learning quite a bit from ENSO, which is I find interesting. And so the takeaway is essentially the same for precipitation and surface pressure. So again, I'm showing the RMSE on the left and the ratio of RMSE and the internal standard deviation on the right. And so again, we get higher scale in the tropics for both of these variables. In these cases, we also see in the mid-latitudes, there's some regions where we're getting, actually the AI model is doing a little bit worse than noise. So this is something that I'm trying to figure out why that's happening, but it is something to keep in mind as we look at some of the projections of climate responses. And so in order to, we see that the AI model is able to fairly reasonably project the noise in the CSM2 data. And so the real test here is to see if the model can reproduce the response of the climate system to some external forcing. And so here we're using some CSM2 simulation data that we generated in a parallel project where we ran a set of CSM2 MCB experiments where we've increased the cloud droplet number concentrations to 600 per centimeter cubed in 3 regions. The Northeast Pacific, Southeast Pacific, and Southeast Atlantic here in the subtropics. And so these are sort of like G4 simulations from GeoMIP, where we have some global warming background state, in our case, SSP 245. And then we just simply impose the MCB at 2015 and hold it constant until 2065. And so we take the MCB effect as the difference between the SSP 245 and the MCB perturb simulations. Okay. And then in order to generate the AI projections, we use radiation anomalies from CSM2 fixed SST simulations. So that means that the forcings that we're using are the MCB effective radiative forcing. And so since we're just changing CDNC, the bulk of the anomaly is, of course, in the cloud shortwave effect. And I guess one thing to note is that these two, the CRES and CRES SIRF anomalies, fall within the 2 sigma range of the internal variability. And so I think we can say that at the very least, these anomalies are not too far outside of what the model has already seen. Okay, so here are some results from our AI FDT model. So on the left, I'm showing the CSM2 response to MCB forcing in the 3 regions. And then on the right, I'm showing the time-integrated AI model response for those same forcings. And so we see that here, the spatial correlation score is about 0.8. So the AI model is reproducing the pattern of temperature response fairly well. But we also see that it's substantially overestimating the magnitude of the temperature response. But, you know, I think it's quite nice here that we're getting this pretty clear La Nina-like temperature response to MCB, similar to what we see in the case of CSM2. Okay, and then the story is again similar for precipitation and surface pressure, but again, so the patterns are looking okay, pretty good. We are capturing a lot of regional details that I think mean that the method is showing some promise, but again, the magnitudes are much too large. But you can see, for example, the AI method is correctly identifying that the Southeast Atlantic forcing here is causing drying in the Amazon, for example, and an increase in precipitation over West Africa, as well as the Southeast Pacific is causing increases in Indian monsoon and Australian monsoon rainfall as well. And so, I'm running out of time, so I'll just say the main point here is that most of the overestimation is because of the Northeast Pacific sector. Actually, the magnitude differences are not so bad for the Southeast Pacific and Southeast Atlantic. And then we do see, if we take a look at the Southeast Atlantic, we're seeing something like a Atlantic Nina temperature response. And so this does suggest that the AI model is learning non-ENSO signals, so it's not completely being dominated by the ENSO effect, which is nice. And so just to summarize, we've been able to combine, you know, FDD principles with AI techniques, and this sort of method seems to show promise for projecting climate responses to marine cloud brightening. And so our model is able to fairly skillfully project the pattern of climate response to MCB, but it pretty substantially overestimates the magnitude of the response. And the nice thing here is that the AI model takes about 100 seconds or about a minute to run a given projection. And, you know, this is several orders of magnitude faster than a GCM projection. And so the idea is that maybe we can use a tool like this in order to identify potentially interesting scenarios for future SRM GCM's experiments. So this work it was just accepted for the AAAI Symposium, which is American Association for Artificial Intelligence. And so we have a preprint up on arXiv if you're interested.
Fantastic. Thank you, Haruki. And does anyone have questions? I'll start if I may. Have you thought more about how we could use similar techniques for SAI? I appreciate there are like differences in time scales and spatial scales, but maybe you can like learn something for SAI as well.
Yeah, absolutely. I think there's certainly no reason why this FDT method wouldn't work for SAI. So I guess, yeah, so that's something that I'd really be interested in taking a look at, is see if we can get our method to work not just for MCB, but also for SAI as well as greenhouse gas forcing, and make a more versatile tool, I suppose, for exploring forcing scenarios.
Great, yeah. Hongwei, do you have a question?
Yes, very nice talk, Haruki. So I have questions about the input data for the AI model.
Sure.
So can you see a little bit the rationale, like how you select those input? Like, would the AI model results better if we have more input, and also have you checked the contribution or power of each input file for the final results?
Yeah, so this is something that we definitely need to explore further, is trying to understand what exactly what exactly the model is learning from these input variables. So that would, I think, be a great I think that would fall under the umbrella of explainable AI. Just to on the note of how we chose these these input variables, originally we were hoping to apply a physical constraints. So we can calculate, for example, the total radiation and heat. I guess it would, yeah. So the idea we were hoping was to compute the atmospheric heat and radiation budget, and make sure that and essentially penalize the model during training for violating it. And so that's why we have this set of surface radiation variables that sort of covers the entire budget at the surface and top of atmosphere. And so, but essentially during testing, we found that it's quite difficult to actually in practice impose these physical constraints. And we do find that actually, even if we only consider the TOA variables here, we're getting pretty similar results. So I think, this is something that I guess AI people are quite used to thinking about, is you do need to be quite judicious about how you choose your input variables. And so it does seem like there's a little bit of sensitivity of the results to the input variables. So yeah, that's something that we need to, I think, more carefully explore in some future analysis.
Simone? No, go ahead.
Yeah, I can quickly ask. Also, a very nice talk. And my question was if you could explain why the signal was much stronger in the artificial intelligence case.
Yeah, so this is I've been trying to figure that out, and I've made a little bit of progress, but I think we're still we still haven't figured out exactly why this is. So you can see here that actually, if we take a look at individually the Southeast Pacific and Southeast Atlantic, the magnitude error is not too bad, but it's really this Northeast Pacific case where the magnitude error is coming into play. And so perhaps what's happening is that the AI model is perhaps overweighting the importance of ENSO. So, obviously ENSO is a big part of the internal variability, but maybe in the case of the Northeast Pacific, it's not as like that mode of, the forcing is not activating that mode of variability in the GCM as much as it is in the AI model. So perhaps we need to be a bit more careful about, maybe pre-processing the data to, so that ENSO is not as dominant as a mode of variability. That's one hypothesis. I guess another hypothesis would be, or another method might be, just to increase the number of nodes in the AI model. I think that's the, we can brute force it and hope that by adding more neurons, then, then the model will be learning more modes of variability, and maybe that will improve the magnitude performance. I guess the short answer is I don't know, really.
Yeah, and any feedbacks that may be not captured by this method could be also included, right?
Yeah. I guess the, so absolutely. I guess the hope of FDT is that, because we're training on this internal variability, the sort of all the necessary feedbacks are implicitly included in the training and therefore in the model. But that's a pretty big assumption to be making.
So Michael, do you want to ask a question?
Yeah, really nice talk, Haruki. One thing I was kind of struck by, maybe this is just because I'm only seeing it for the first time and haven't caught all the differences, but it looks like everything's adding surprisingly linearly when you add all three together in terms of the global mean, and then also regionally, it looks like the responses are pretty much just superimposing linearly. I guess, is that true? And do you expect it to change if you tried something with like more regions or something? It'd be very convenient if that were true. It just seems surprising.
Yeah, well, so I guess for the CSM2 simulations, I'll just go to this figure here, which is the global mean surface temperature. And so actually this green line here is the sum of the different regional perturbations, and the solid blue lines are where we're imposing the forcing in all three regions at once. And so there is, it is subtle, but there is a little bit of a nonlinearity here. So it's not quite additive in CSM2. But yeah, it is pretty additive, which is nice. And in the case of the AI, I think, it's perhaps even more additive. I haven't actually done the statistics for that, but yeah. So I don't know, maybe it just looks more additive than it is because we're getting such a large contribution from just one of the regions, but it does seem like we're getting pretty good additivity between the three regions we're testing at least.
Okay, we've reached the end of the hour, so I think we'll keep it there. So thanks again to Haruki and Susanne for your great talks. If you want to give a talk again, please reach out to me or Simone Tilms, and we'd be glad to have you. So see you.
Yeah, for having me.
Thank you.